For the first cut, although your book will do the second cut, is tryptophan, tyrosine, phenylalanine, chymotrypsin is a protease. And it is a member of the class of proteins referred to as serine proteases. So when you see a biochemical term that ends in ASE, usually you're dealing with an enzyme. It ends in ASE, and then the prefix, the first part of it, will tell you the substrate. So a protease is an enzyme, and the substrate for the enzyme is a protein. So chymotrypsin is an enzyme that will act on proteins. It will look for a tryptophan, make a cut of a peptide bond after that tryptophan. It will look for tyrosine, make a cut after the peptide bond for that tyrosine. Phenylalanine, make a cut. And the reason they're called serine proteases, okay? They're called a serine protease because what we will see is that the enzyme, the chymotrypsin, has a serine in the active site, and that serine is going to make a covalent bond with the substrate. Without that serine, you don't get the covalent bond with the substrate, you don't get activity. So a serine protease is an enzyme where you have in the active site a serine that will make a covalent bond with a substrate, and you have to have that covalent bond in order to have activity. Now, let's do an abbreviation of the substrate just for convenience. So let's look at a protein chain, and I'm going to say R. Okay. And then you will have the amino acid that has the side chain to be recognized. So let's say C, H, and let's make this the W side chain that's recognized. Then we're going to have the carbonyl. Then we're going to have the nitrogen. And then we're going to have, let's say, R prime. Okay. Now, what we want to focus on is the amino acid that's recognized, which is this. And I'm using R and R prime just for shorthand purposes so that we can focus on either the tryptophan, or this could be tyrosine, or this could be phenylalanine. Because we're going to need to abbreviate this in order to do the mechanism. The bond that's going to be broken is the peptide bond after the amino acid that's recognized. So whether this is tryptophan or tyrosine or phenylalanine, we're going to break the peptide bond after the side chain, which is this. So here's the side chain that's recognized. It could be tryptophan, it could be tyrosine, it could be phenylalanine, and then right after it is this peptide bond. That's the bond that chymotrypsin is going to break. When chymotrypsin breaks that bond, this carbonyl is going to become a free carboxyl group. This carbonyl is going to become a free carboxyl group. This nitrogen with the hydrogen there, it already has a hydrogen. This is going to become a free amino group. So the focus is right here. And because the focus is right here, we're going to do an abbreviation of everything else. So we're going to keep this as R prime. And now, although the tryptophan is here, we're going to rewrite all of this and make it R. And you have to understand that the side chain for the amino acid that's recognized is part of R. And the reason we're doing this is just to save space and drawing out the mechanism. Just to save space and drawing out the mechanism. So I'm going to redo this, and I'm just going to put R right here, and you understand R will include the amino acid side chain that's recognized. Okay. Now, the other thing that I know from experience, our drawing will be easier to do if we write this in the reverse order. In other words, when we get ready to do the mechanism, we're going to have R prime, then the nitrogen, put the hydrogen up, then the carbonyl with the oxygen up, then R. This is now our substrate. That's the best way to draw the substrate so that you have the space. It doesn't get too crowded, too messy in practicing the mechanism. Any questions on how I got to this as the substrate? Okay, so now we're going to erase all of this. Let's just clear. Okay. Let's look at the active site. And we get our substrate. And so we said for the substrate, we had R prime, we had N, we had a hydrogen up here, we had the carbon, the oxygen up here, and then R. That's our substrate. Now, the active site, there's some features of the active site that we need to be aware of. First of all, and actually your book does a very good job of explaining this. In the 9th edition, it's on page 242. In the 9th edition, it's on page 242. Okay. So the active site is a 3D cleft. It's internal, a cleft or a crevice. Okay, we'll see that when we do the mechanism. Also, with respect to size, volume is small relative to the total enzyme. Small relative to the total volume of the enzyme. It's unique microenvironment. the enzyme plus substrate, in other words, the binding, is due to those weak non-covalent interactions. Okay? Those weak non-covalent interactions, like hydrogen bonding. Okay. Okay, yes. And lastly, specificity. This is based on the 3D arrangement of atoms. And we'll see this when we look at the active site of chymotrypsin. All right, any questions there? There are certain catalytic principles. What I just said about the active site, that's in chapter 8. Now we're moving to chapter 9. So catalytic principles. And one of the reasons we do chymotrypsin is because most of these principles come to play in chymotrypsin. One is flexibility. In other words, when the protein, the enzyme is made, it is not so compressed that the substrate can't diffuse into the active site. The substrate must be able to diffuse because the active site is internal. Okay? It's internal. The substrate must be able to diffuse into the active site, and then once the substrate is in the active site, the enzyme is going to clamp down on it. The enzyme is going to clamp down on it, and in order for the enzyme to clamp down on the substrate, the enzyme must be flexible. The enzyme must be flexible. That also brings to mind that in a chemical reaction, in order for the reaction to take place, atoms must collide. Okay? And in biochemistry, we call that the proximity effect. Okay? We will also see is that, again, with this unique microenvironment where you have weak non-covalent interactions, we're going to see attractive forces that stabilize the substrate in the active site. Okay? And we're going to see attractive forces, and that's going to lead to stable binding. One of the principles in enzyme catalysis is that there usually is a side chain that can donate a hydrogen or accept a hydrogen in order to facilitate the mechanism. So we call that in biochemistry general acid and by general acid we mean donate general base and by that we mean accept catalysis. So general acid catalysis, we'll have a group that will donate a hydrogen. General base catalysis, we'll have a group that will accept a hydrogen. 5, we will have groups that can serve as nucleophile, electrophile. Okay. So we can see nucleophilic, we will see a nucleophile, and we will see that it will attack part of the substrate. Okay. 6, this is the last one. Electron rearrangement. Now, all of these are present in chymotrypsin. There's another principle that I'm going to put in brackets, and we will see this when we do another mechanism, and this is metal attack. This is not in chymotrypsin. We will do another mechanism, and we will see attack that is facilitated by a metal. So we'll call that metal catalysis. Now, the way I have written them, 1 through 6, if you learn the principles and you learn them in that order, it will help you to learn the mechanism of chymotrypsin. Because 1 through 6 will be used in the mechanism of chymotrypsin. And if you learn them in that order, it will help you to learn the mechanism, because that's the order in which they will be used for chymotrypsin. 1 through 6. Any questions? All right. So now what I'm going to do now is focus on the active site of chymotrypsin so that we can learn the mechanism. So we're going to see chymotrypsin. Here's an enzyme, all of that. Okay. But the active site is going to be in here. And so I'm going to do a blow up of the active site. I'm not going to focus on the whole protein. I'm just going to do a blow up of the active site so that we can learn the mechanism. So again, let's we're going to do a blow up of the active site. So this is just a blow up of the active site. And in the active site, we're going to focus on 3 amino acids, and we're really going to look at their side chain. Here is an aspartic acid. Let me give you the numbers. It's in your book. So we have the catalytic triad is aspartic acid 102, histidine 57, serine 95. So this is the aspartic acid. Okay, and that's 102. And then we have histidine 57. Histidine. $57. Then here is the serine, 95. 195. So here's how I want you to learn the mechanism. I want you to start with the active site, the way I have it drawn, no substrate. Then you're going to bring in the substrate. You're going to do the mechanism. You're going to have the substrate leave. You're going to have an empty active site just like this. For each step, look at those 6 catalytic principles and identify which principle is being used for each of the individual steps. So for instance, when the active site is empty, this is what we have going on. I'm going to draw a hydrogen bond between this oxygen and this hydrogen. Okay. Hydrogen bond. Because this oxygen is partially negative, this hydrogen is partially positive. So that's a hydrogen bond. Over on this side, this hydrogen is partially positive. This nitrogen is partially negative. So we have a hydrogen bond here. Now what you have to do, and I'm not doing a very good job of it, what you have to do is come up with a way so that I know and you know the lines between 2 atoms like this, representing a covalent bond, and the lines between that represent your hydrogen bonds, dashes, are different. Okay. So maybe what I can do is do vertical. So let's redo that. Because it needs to be clear what is a covalent bond and what is a hydrogen bond. Okay, so put this back. So here's my hydrogen bond. Now that is different than this line, which is a covalent bond. So make that distinction when you do your practicing. Your hydrogen bond and your covalent bond must look different. So that's the empty active site. Now I want you to notice something. I told you that chymotrypsin is a serine protease. There must be a covalent bond between the serine and the substrate, which is going to go right here. We're going to put the substrate right here. If this covalent bond does not take place, then the enzyme is not active. The mechanism won't take place. In order for the serine to make a covalent bond with the substrate, which is going to be here, this serine must lose this hydrogen. This serine is going to lose this hydrogen because the histidine, with this long pair of electrons, this histidine is going to act as a general base and form a new covalent bond with this hydrogen. And that's how the serine is going to be able to make a covalent bond with the substrate. So the serine must lose this hydrogen. The only way the serine is going to lose this hydrogen is for this nitrogen with a long pair of electrons, not this nitrogen that has a hydrogen bonded to it, but this nitrogen with the long pair of electrons must come close enough to this hydrogen to form a new covalent bond. And in order for that to happen, this histidine must be locked in this orientation. Okay, plane of the board, it must be locked in this orientation. If it was flipped 180 degrees, then this nitrogen with this hydrogen with a partial positive charge would be facing a hydrogen with a partial positive charge, and this hydrogen would not be lost. So the only way for this to happen is for the histidine to be locked in this orientation, and that's what this aspartic acid does. Because this aspartic acid would not form a hydrogen bond with this nitrogen, because this is partial negative on the nitrogen, this is partial negative on the hydrogen. So the fact that this aspartic acid is here, it locks this histidine in this orientation such that the side of histidine with the nitrogen and the hydrogen with the partial positive is facing this aspartic acid. So that's the stabilization of the active site based on hydrogen bonding, electrostatic interactions. Is everybody okay with that? So the empty active site with aspartic acid 102, histidine 57, serine 195 is stabilized based on hydrogen bonding, the carboxyl group, and the histidine, because this oxygen is partial negative, this hydrogen partial positive, they form a hydrogen bond. And then this histidine serine hydrogen bond is based on this nitrogen partial negative, this hydrogen partial positive. So that's the explanation of how electrostatic interactions stabilize the active site, the catalytic triad that makes up the active site, even before the substrate comes in. Okay, now let's go through the mechanism. So the substrate is going to diffuse into the active site. And I'm going to put the substrate right here, because I know the serine needs to make a covalent bond with the substrate. So I'm going to put the substrate right above the serine. So again, the enzyme is flexible enough so that as the substrate diffuses in, it opens up somewhat to welcome the substrate in. But then once the substrate is in the active site, the enzyme is going to clamp down on it. That's flexibility. So let's put the substrate right here. So we have the R, the nitrogen, the hydrogen, the carbonyl, and the rest of the protein. Because remember, this is a protein. So we have the rest of the protein over here. We have the rest of the protein over here. This is what we're going to focus on, the peptide bond right here. So now that the substrate is in the active site, proximity, flexibility, proximity effect come into play, because really they are very close together. They are very close together, very close. They are so close that this nitrogen right here is going to form a new covalent bond with this hydrogen. So I'm going to erase this, and I'm going to make a new covalent bond. I'm going to erase this hydrogen, these dashes, and I'm going to make a new covalent bond here. So the histidine is going to accept the hydrogen from the serine. So the histidine is acting as a general base. So we've already had flexibility. We have established the proximity effect because these are very close together. So what we're going to do now is we're going to remove all of this. We're going to put the hydrogen here. And we're going to put a plus charge here. Because when histidine is protonated, it has a plus charge. Okay. Now, so we had the flexibility, proximity effect, the electrostatic interaction, and now the histidine acts as a general base. Next is nucleophilic attack. The serine is now the nucleophile. Nucleophile is electron rich. It's looking for an atom that is electron deficient. And when we look at this, remember, this is not an atom. This is not an atom. This is a serine. This is the electron rich. This is the electron rich. The nitrogen, the oxygen. What's electron deficient is the carbon. So we're going to do this. The arrow represents the flow of electrons. So the electrons start with the oxygen, and they're going to end up the arrowhead with the carbon. So a mistake that students make in mechanisms is drawing the arrow wrong. Your arrow starts with your electron-rich atom. It's going to end up your arrowhead at the electron deficient. Okay. Any questions? So we're going to have a new bond between the oxygen and the carbon. But now this carbon already has 4 bonds. So what we're going to do in making the new bond, we're going to take the double bond and make it a single bond. So we're going to show the flow of electrons such that we get a negative charge here. So I'm going to erase and make new bonds. So instead of a double bond, it's going to be a single bond. And now we're going to make this a new bond between the carbon and the oxygen. We're going to get rid of this. Okay. And now that oxygen has a negative charge. Any questions so far? Okay, so the histidine acted as a base. It accepted the hydrogen from serine. Serine acted as a nucleophile, formed a new bond, nucleophilic attack on the carbon, because it's electron deficient. Nucleophiles want to share their electrons with electron deficient atoms. That carbon already had 4 bonds, so we did electron rearrangement such that the double bond between the carbon and the oxygen becomes a single bond. Here, now this oxygen with a negative charge. Okay. We're going to, in our next step, do electron rearrangement again. In other words, we're going to take this negative charge and we're going to reform the double bond around this between this carbon and oxygen, and this carbon still has 4 bonds. So we're going to break a bond, but this time we're going to break the bond that facilitates the mechanism. And the breaking of the bond that facilitates the mechanism is to break this bond here. So electron rearrangement, reform double bond. And then break this bond, and we're going to break this bond and accept the hydrogen from the histidine. Okay, so let me erase. So this negative charge goes away. Now we have reformed this double bond. But we can't have 5 bonds around this carbon. So we're going to erase this bond. This nitrogen picked up the hydrogen from the histidine. So electron rearrangement, reform the double bond. Break the carbon-nitrogen bond, which is the goal of the mechanism. Histidine, that was protonated with a positive charge, now is donating. It's a general acid. Donated a hydrogen here. We have formed the NH2, the free amino group. So now this part is ready to leave. The carboxyl part cannot leave because it's still covalently attached to serine, the substrate. So this part can leave. So again, here's the flexibility. Open up enough so the amino group can leave. So I'm going to erase that. Any questions? Okay. That's the first half of the mechanism to release the free amino group. The second half is going to release the free carboxyl group, and it's going to be very similar. When the amino group leaves, water comes in. I did that for a purpose. So now everything we just did in order to release the free amino group, we are now going to do again to release the free carboxyl group. Flexibility allows the free amino group to leave, the water to come in, clamp down, establish the proximity effect, which means that now this nitrogen is so close to this hydrogen that it's going to form a new covalent bond. The OH group from the water will become the new nucleophile that will attack the electron deficient center. Okay. So let's make new bonds. Okay, we're going to erase this. Hydrogen here. Plus charge here. So again, histidine acted as a base. Here's now the OH group. This is the new nucleophile. That's going to attack the carbonyl carbon because that is the electron deficient atom. So I'm going to make a new covalent bond here. The OH group. take some water. Okay. In order for that to happen, because again, the carbon already had 4 bonds, so we do electron rearrangement again, put a negative charge here. So let's erase, instead of a double bond, we have a single bond, just like before. Okay. Electron rearrangement, the carbon-oxygen double bond becomes a carbon-oxygen single bond with the movement of pair of electrons here to give that minus charge. So the next step is again electron rearrangement. We're going to reform the carbon-oxygen double bond. We'll need to break a bond because this carbon already has 4 bonds, and the one that we're going to break is the one that facilitates the mechanism so that we release the free carboxyl end. Okay. So we're going to do electron rearrangement by moving electrons here to reform the double bond. We're going to break this bond, and again, we're going to pick up a hydrogen from here on the histidine to reform the serine. So let me use the eraser. Put this back. Eraser. Put this back. Now we have generated the carboxyl end. This is now free to exit the active site. And it's ready to start all over again. Any questions? Okay, so here's my suggestion. Go through this mechanism in every step. Well, first of all, write out the catalytic principles. Write them out in the order that we went over in class, because that's the order in which the mechanism takes place. So write out the catalytic principles, then go through and draw the mechanism step by step. And for each step, write the number of the catalytic principle that takes place in that step. So for instance, this is the empty active site before anything takes place. We see the active site, the catalytic triad, is stabilized. Go back here, put my partial negative, put my partial positive. This is stabilized by those electrostatic interactions, hydrogen bonding. So each time you have a step, you should be able to identify principles that take place in that step and identify the number and just write it. Continue to do that until you get to the point where you don't need your textbook, your notes, or anything. Practice makes perfect. You want to be able to take a blank sheet of paper, and from that blank sheet of paper, without the book, without your notes, without anything, write out the 6 principles, go through the mechanism, and identify with each step what principle takes place. So here are the mistakes that will take place if you don't practice the way you ought to. You'll start making simple mistakes. You'll miss the structure of histidine. That's a simple mistake that students make. You'll protonate histidine, not put the positive charge. Simple mistake. You'll not draw the substrate right. But if you practice this, because practice makes perfect, you'll get it. Because chapter 9 is all about mechanisms. So that's what I suggest you do until you can do it on a blank sheet of paper, without the book, without your notes, or without anything. Any questions? Any questions? Okay, we'll stop there today. What we will do Thursday is the other mechanisms are not as detailed. If you learn the mechanism for chymotrypsin, it will make the other mechanisms very easy. So go ahead, learn the mechanism for chymotrypsin. You practice it, it will click. And then Thursday, we will finish chapter 9. We will move on to chapter 10. I believe the next exam stops at 10, or does it cover 11? I don't remember. I didn't check the syllabus this morning, but we can use Tuesday as a review because remember, all of the exams are comprehensive. All of the exams are cumulative. So exam 1 will be covered on exam 2, the information. So we will finish chapter 9. We will go over chapter 10. I'll check the syllabus to make sure I know whether it's 10 or 11, and then we'll go from there. Any questions? I need Mr. Ruby to stay on. If there are no questions, then have a good day. I need Mr. Ruby, Brian Ruby, to stay on, and I'll see the rest of you on Thursday.